I want to thank everyone for taking the time today to join me for a discussion about the new J3 DentaJet, which is an implantology powerhouse. My name is Richard Cromwell. I'm a senior applications engineer and dental AM application specialist at GoEngineer. I'm based out of the Metro Detroit, Michigan region. I work at the Pleasant Ridge office where I have a collection of dental machines, including a DentaJet and an Origin One dental, so that I can print dental benchmarks and parts for our customers. You might be asking, who is GoEngineer? We've been in the business of helping our customers to bring their products to market by utilizing the latest technology solutions for design and digital manufacturing. We work with some large customers, as you can see. Our focus is on making sure that the customers that purchase equipment from GoEngineer are able to successfully deploy that equipment and effectively incorporate it into their workflows. We are a large organization with 60 offices spread across the entire continent of North America. And we are the largest SolidWorks reseller in the world and also the largest Stratasys 3D printer reseller in the world. So who is Stratasys? Stratasys has been a pioneer in additive manufacturing for over 30 years. They were the guys who originally developed the second oldest form of additive manufacturing, which is fused deposition modeling. Imagine the stereotypical glue gun on a gantry 3D printing, only they have perfected it at an industrial scale. I like this timeline. I like to point out that even though it's not a name that a lot of people in the dental industry are super familiar with, Stratasys is very familiar in industries like aerospace and medical device and transportation, things like that. But inside of dental labs, which is primarily dominated by lower level 3D printers, Stratasys' history of working in the dental industry goes back to 2009 when they launched the Objet Eden 260V. And then there was kind of like a lull in dental development on Stratasys' side until about 2020. And then things really started to change and they started to ramp up and develop new machines and new technologies, new applications specifically for the dental industry. And this is great because it allows the dental industry to take advantage of the experience and the depth of knowledge that Stratasys brings to additive manufacturing.
The dental industry is constantly evolving, advancing, developing. To be the best, you need the best. Stratasys Dental, because we leveraged 30 years of additive manufacturing experience with the best of 3D printing technology and adapted it for the dental industry, offering multi-material printing with extremely accurate parts. The world's first monolithic full-color appliances, and next-generation DLP technology, featuring higher throughput, remarkable surface quality. We're pushing the boundaries of digital dentistry, providing GrabCAD print, an intuitive software platform, delivering a smarter, smoother workflow. Dental is our priority. We are driven by your need to keep production going. Stratasys, your partner for smart growth. Stratasys Dental. Master the challenge.
I want to frame this discussion primarily through the lens of looking at implantology case planning, because the DentaJet series is actually capable of doing a lot of different things. It is not the end-all be-all cure to every dental application, but it is a powerful machine in a very compact footprint and at a cost that gives small and medium dental labs PolyJet multi-material technology that before was probably a bit out of their price range. So it's a novel solution. I also want to point out that this is a webinar that is open to general population. And so not everybody is going to know about implantology. So just real quick, if you have a patient that has serious dental issues, perhaps they're edentulous, they don't have any teeth, a workflow that we use today, and it's highly digitized, where we're taking medical imaging data and combining it with 3D CAD data to be able to do precise planning of how we're going to approach installing the implants into a patient's mouth so that we can then attach the external portion of the implant. This involves drilling into the bone of the patient. You can see here where these are installed, and then you can also see the connections for the interface on the device. And so these are implant secured dentures. And so there's the lady's smile. It doesn't necessarily always have to be replacing all of your teeth. Sometimes we're just replacing one. And where 3D printing really comes into play here is with the printing of surgical guides. This is a surgical guide that's printed out of Med 610, which is a biocompatible clear material that's available on PolyJet systems. And then you can see here how it's being utilized in the patient's mouth. They use metal collars as drill bushing guides and just go right into the patient's bone there. So the idea is that through 3D printing, and specifically with PolyJet, we can simplify the complexity of implantology and maximize the production of our parts. But we can also print opaque and rigid implant models, biocompatible and transparent surgical guides, and soft gingiva masks all on one tray in a single unattended print job in one step. And so the solution that we're really presenting here with the DentaJet, and there's two different versions, is a complete game changer. It's something totally different than what a lot of labs and a lot of lab technicians are used to working with. While there are two different versions of the DentaJet, the J5, which is kind of like the big brother, it has a material cabinet beneath it. Today, we're going to be talking about the J3 DentaJet, which is a very similar machine. It's essentially the same platform, but it doesn't have the material cabinet. It just uses the same material cartridges, the same 1.1 kilogram cartridges, but it is a much smaller, more compact, and of course, less expensive machine. One of the things that makes it different than most of the printers out there is that it's not using a Cartesian axis, and it's not using like what we'll see in vat photopolymerization technology, where it's using a build head that's lowered down into a vat of resin. This is using a polar axis, a circular platen that rotates under a print head that can only move on one axis. So mechanically, it's a much more simple machine than the legacy big box Cartesian axis PolyJet systems of the past. For those of you out there that are familiar with DLP printing and open vat photopolymerization for dental applications, PolyJet might not be a technology that you're super familiar with. If we look at the classifications for additive manufacturing from ASTM, this is a technology that is going to be categorized as material jetting. It uses a piezoelectric print head to jet microscopic droplets of UV photopolymer resin onto a build tray, and it just builds up layer by layer using these microscopic droplets. If we look at the statistics, 87% of dental labs are using vat photopolymerization technology, 13% are using material extrusion, 10% powder bed fusion, and only 8% are using material jetting. I think that today we'll be able to present some compelling information that will cause the dental industry to shift that ratio and increase the number of material jetting systems out there, because it is such a great solution for dental labs. If we take a look at all of the dental printers on the market, and these are all of the new printers that are available today by AM classification. This is just information that I was able to glean from LMT magazine, because they have a buyer's guide that they put out every year. And so there are 24 open vat photopolymerization technologies, and then there were two material jetting systems that were released and published in this document. And both of those are DentaJets. One's the J5 and one's the J3. And so between these two slides, you can see that DLP and other forms of open vat photopolymerization are very popular. And it's because of the accuracy over things like FDM. So PolyJet is a unique solution that comes from Stratasys that isn't really duplicated by anybody else on the market today. If you're not familiar with top-down processes, what is happening is quite a bit different than what we do with a PolyJet system, where we have these print heads that are ejecting microscopic droplets of resin. Instead, they will lower a print head down to a vat of resin, and then it uses various forms of light, either a projector or a laser, to trace the vectors and rasters, the perimeter of the images of the parts onto the pool of resin, and then it will raise it up a tiny fraction of an inch, maybe 100 microns is pretty standard. And then it will do the next layer and then another 100 microns up and then the next layer. For comparative analysis sake, when we look at a PolyJet system like the J3 DentaJet, that layer resolution, which is a critical factor in the accuracy of the prints that we produce, the layer resolution for the DentaJet is 18.75 microns. So it's typically 4 to 5 times as accurate. So this little video is going to show the J5 platform. A lot of people are familiar with PolyJet. They're familiar with the big box Cartesian systems and not with this polar axis concept. There you can see the print head lowering down to build tray, and actually the build tray is coming up to it. And now it's ejecting multiple materials. They have PolyJet systems that can print up to 8 materials plus support material. The J55 can print 5 materials, and the J35 can print 3 materials. You can see we have a stand for the little machine here, or you can put it on a countertop. You don't need to use the stand. It takes 3 materials at the same time, and there's different material schemes that you can load, and I'll show you that in a little bit when I get to the software. There's 2 speeds right now, high quality speed and high quality high speed. There's going to be a super high speed coming soon. And again, the primary application that we're looking at for today, just for comparative analysis sake, to compare other machines and systems, we're going to stick within the realm of surgical planning guides. But there are many other indications and applications that you could use this printer for beyond that, including dental models, try-ins, surgical planning models, castable partial frameworks. I think that's a really neat application using Med 610. Let's get into what problems does the J3 DentaJet help dental labs to solve, right? What are we really trying to achieve? It's not just that it's a cool looking printer that spins in a circle. It actually brings tremendous value to your operation. And so those of you that are out there running DLP systems understand that most high-end DLP systems have small build trays. This means that you can't really print a lot of parts at once in one build. You can be like relatively creative with orientation and support structure generation in order to be able to pack as many parts as you can onto the tray, but it's still very small and very few. If we look at just a handful of popular 3D printers that dental labs use, and this is all public information, if we look at all of these printers, the blue represents the estimated cost of the printers. And some of them go from, like, what do we have here? About $10,000 all the way up to a Carbon M3 Max, which is like at $225,000. Now, I got to put a little asterisk next to that because, you know, you can't buy a Carbon printer. You can only lease them. And the minimum lease is 3 years. And like the minimum lease overall payment for the entire term, I think, is around $225,000. And so it's a very expensive printer. And then I took the tray area. The bigger the surface area, the more models you can print at once. And if we look at the surface area of all these different printers, which is represented by this blue line here, the Stratasys J3 DentaJet has a much larger area than any of the other printers. And so if we take this a step further and we factor in the cost of the machine and how much tray area each machine has that you can print parts on, what are you paying for in terms of cost per centimeter squared? And it's fascinating that between all of these printers, including the $225,000 one and the $10,000 one, the cost per centimeter squared for the Stratasys J3 DentaJet is by far and away the lowest. And so this shows us that the Stratasys, in terms of production, based on this metric, represents a great value for your dollar. So what's another concern that we have when running DLP printers? DLP printing is completed quickly and with very few parts on the tray. So why is that such a big problem? Well, we can look at it this way. If you have another popular DLP printer, it has a build tray of 264 centimeters. We can fit 10 quadrant models and arches on here. The print time would be about 1 hour and 37 minutes. So if we break it down to minutes per part, we're at 9.7 minutes per part. Let's say that we take a J3 DentaJet with our giant build tray and we use the intelligent software that is inside of GrabCAD Print, which is the build prep software for Stratasys machines. How many of these parts can we print and maximize the utility of our printer to reduce the minutes per part? And so we could print up to 52 models in 2 hours and 57 minutes, which gives us 3.4 minutes per part. What problems does the J3 DentaJet help dental labs to solve? What about requiring continuous handling to get to a larger volume with P3 or DLP? In the last slide, we were talking about how the parts print very quickly and there's not a lot of them. And so you have to factor in that you're going to be walking up to this machine every hour and 37 minutes when it's done printing 10 parts. And you're going to have to go through the workflow of post-processing these parts. And with DLP and SLA and other open vat technologies, that's a very hands-on process. It's messy. You're exposed to uncured resin, which is dangerous. And overall, it's just not the most pleasant workflow. Where with PolyJet, it is a closed material system in terms that the materials all are in cartridges. And the waste is emptied into a waste container. And so operators are generally not exposed to uncured photopolymer resin. It is so much more pleasant to be working with PolyJet systems than it is with open vat photopolymerization, just from that alone. This comes into play, especially with surgical implantology planning cases. So with a DLP system, if we're going to print a case, we need to use 3 different materials. One is for the model, one is for the surgical guide, and then the key mask is a soft material that you use for the gingiva mask. And so if we break down what it's like to print just 2 cases, so we're looking at 4 models, the upper and the lower for each case, 6 gingiva masks in a soft material, and then 2 surgical guides in a biocompatible clear material. So we printed this on 2 different systems, the J3 DentaJet and a popular DLP technology. With DLP, you have to mix the resins up, and some resins are 2-part resins, some are single component resins. I prefer the single component because then you can put them back in the bottle. Usually they have a better shelf life. The 2-part, once you add the catalyst, it's go time, and then whatever you have left, go to processing for industrial waste. Another thing that you have to consider when we're using DLP technology is that you have to nest all of the parts intelligently. You have to orient the parts. You have to run support generation. This takes a lot of skill and practice. You have to know what you're doing to have successful builds. So that can be time consuming, and 30 minutes is pretty typical, I think, for something like that. On this machine, they had to print the models in 2 builds. You have to wash the parts in isopropyl alcohol, where you're going to wash it for 2 minutes, take the part out, look at it, see if there's any shiny resin still on it. If there is, you got to wash it again. And you keep doing that process until you're sure that there's no more uncured resin on the part. You have to let it dry, because after being in isopropyl alcohol, we can't just throw it into a post-cure UV light cabinet, because that could be dangerous with the flashpoint of IPA. We need to do these steps for each of the 3 different types of models, because we can't print them together. They're all different materials. We have to use the model material for the implant model, the soft pink material for the gingiva mask, and then the clear biocompatible material for the surgical guide. Each one's going to have its own support mechanisms. You have to mix the resin over again. So total time for printing and post-processing for just 2 cases using this DLP technology that people use every day in the dental world was 7 hours and 16 minutes. So you're looking at total hands-on labor from a technician that probably could be doing other things of more value. That total labor is going to be 1 hour and 15 minutes. And it doesn't matter if we're printing 1 case or 2 cases, everything essentially stays the same. With a DentaJet, with the same 2 cases, the same geometry, the print time total for everything was 2 hours and 35 minutes. Build preparation, so simple, it's probably 5 minutes tops. The post-processing is so much more simple, less hands-on with PolyJet, that it was only 10 minutes of the technician's time. And here's the other cool thing. If we were going to print a single case, because of the polar axis, throughput on a J5 platform is not linear. The time does not increase or decrease necessarily based on the number of parts, but how the parts are oriented on the build platform. And so the minimum number of parts using the same track that we have in this build, even if we printed 1 part, it would only reduce the print time by 15 minutes, but it'd still be so much less than the comparative scenario. Accuracy and ease of use with DLP technology is definitely a concern, as the partial curing of the parts in the DLP process leaves the parts green. So they have a tendency to warp between being printed and being UV cured. When I say that the parts are green, that means that we can't fully cure the parts that are printed in a DLP or SLA system in the vat for a bunch of reasons. We have to try to apply just the amount of energy to the resin to get it to catalyze to a state that is not fully hardened, but still pliable slightly. This will allow it to have enough strength and not be brittle so that when it pulls up from the membrane, it doesn't break the part. And that's just one reason. There's a bunch of other reasons. Anyway, when we look at a part like this printed on a DLP system, these parts are still green. They haven't been removed from the build tray just based on the geometry of this part. And it makes me nervous that even removing these parts from the build tray or the support mechanism from the model itself could potentially break. And then we have to start over. With PolyJet, we have a completely different situation where there are no support structures actually attached to the part. We use a separate support matrix that is printed in tandem with the model material. As you'll see, it is very easy to remove. The other issue with these DLP supports, everywhere where there is an interface between the support structure and the model, it introduces a potential for dimensional error, because that'll be broken away, and then those nubs that are left on the part have to be sanded away, or people use like a hand piece and a little burr to remove the DLP support nubs. But when you do that, you're potentially altering the dimensional integrity of the part. When we look at PolyJet, that is not an issue because we don't have that type of support structure. Another issue with DLP, and I've alluded to this before, is printing success depends on the user experience and consistency. And that's true. Just as an example, like I was mentioning, DLP, LCD, SLA, you have to manually position the anchors for the supports a lot of the time. And I use automated support generation and automated support scripts in DLP, but you still have to go through and manually move things around. There are some things that we're working on that could mitigate that in the future, but right now that is the case. Where with PolyJet, there is no support mechanism that is actually attached to the part. And so there's no distortion on complex geometries from something like that. You can see here that there's like a gel underneath the model. That's what the support material looks like. And if we take 3D scans of the models that are produced on a PolyJet system, you can see that green is good. And with this heat map, the PolyJet systems hit it out of the park. There was a study that was recently done. It was a white paper. And in that white paper, they identified for surgical guides specifically that PolyJet outperformed every other digital manufacturing methodology that they tested. And it's very widely adopted for that application. Okay, now I'm going to do something neat. I'm going to show you GrabCAD Print. This is the build preparation software that is pretty much universal now for all Stratasys technologies, except for the Neo SLA system. But you can see I just brought in an implantology case here. We have the surgical guide, some gingiva masks, and we have the models. Now, one of the great things about GrabCAD Print is that it has a powerful file repair algorithm. Sometimes when you import files, there might be intersecting triangles and open faces and inverted normals. So this can detect all of that and quickly repair the parts. So that was it. That's all we had to do. And we can see the parts here on the tray. When it comes to the materials, this is how you load the materials. For this, we'll load Med 610. Med 625 Flex is like the flexible biocompatible material. And then we'll load Med 620, which is model material. Now we can apply the materials to the parts. We can shift and click on the gingiva masks. And we'll just make sure those are already in Ferroglaze. There's some intelligent tray utilization features now in GrabCAD that are specific to the DentaJet. And you can set up for different goals, whether it's shortest time per part or shortest tray build time. Today, we're just going to go with the default. We can just arrange the tray. But just to show you how quick and how simple this is and how powerful it is, there you go. It just set it up. And we can go down here and we can get an estimate as to how much print time it's going to take and material usage. So it's 2 hours, 17 minutes. Tells us how much model material, how much support. So it's as simple as that. And whether we're dealing with one implantology case or a whole host of them, this software it's just really easy to make it happen. This is what I was alluding to in terms of how we can set up different trays to achieve different goals. If we just want to have a quick tray with Med 610 surgical guides, we can print up to 6 guides in just 37 minutes. We could also do a lowest time per part, which is about 3 minutes per part, 46 guides in 2 hours and 19 minutes. And then we could do a full tray, up to 61 guides, 3 hours and 28 minutes. So total, based on a 10-hour working day and an overnight tray, we can print up to 245 guides per day at a cost per guide of $3.08, which a lot of you out there would know that's a really good cost per part. So here's another issue when it comes to DLP printing. It's a very messy process. It can be. And I'm fastidious about being clean about it. I love to keep my work area super clean. You have to soak the parts in IPA, usually in an ultrasonic cleaner. And we're going to go through that workflow multiple times to get as much resin off of the parts as possible. Then you're going to let the part dry. And then you're going to cure it in a UV cure oven. And different resins have different times, but it might be like 2 minutes aside. It might be 10 minutes. It just depends. The other thing that isn't mentioned in this slide, though, is the support removal. Some people like to take the support off of models right after they come out of the printer because they want to get as much resin off of the model before it goes into the dirty IPA bath to be clean, because they want to be able to use their IPA bath for as long as possible. And reducing the amount of contamination from the resin is one way of doing that. Personally, I think removing supports from a model that still has resin all over it is kind of a big mess and it's hard to do. I prefer to clean the models first and then remove the supports and then do a post-cure. And if required, you have to go back and remove any additional support, nubs or material, or after the post-cure. So, I mean, it's a long process comparatively to the DentaJet, which I'll show you this super short video. This is what it looks like when we remove support from a PolyJet part. We just take a water jet and blast it off. It takes minutes and it's easy. If anybody has any questions, this would be a good time to ask them. In closing, I want to thank everybody again for taking the time to look at this solution with me. I hope that I might have planted the seeds that will change the trajectory of the dental industry in the future away from using consumer and prosumer level DLP and SLA systems and start to embrace the higher end industrial solutions that are available from GoEngineer and Stratasys.